All right, everybody, we're live. We still have a few minutes before class officially starts, but I figured I should make sure I could get this to work. You want to comment in the chat if you're excited for? Oh, we've lost a viewer since I've gone live. You want to comment something in the chat just to say you're excited for online teaching or online learning? Oh, look at this, 17 viewers. Oh, this is awesome. Down to 15. All right, so we're going to be on a roller coaster. I got to just not look at the view count. We got some hellos. There's a little bit of a delay between the chat and Dr. Y is in the house. There's a little bit of a delay between the chat and what I say, but we'll make it work. Okay, a couple more minutes or about 30 more seconds, and then we could get started. But this is our setup until it's not our setup anymore. If this works out well, then this will be the setup for the rest of the semester. If it works out not so well, then maybe we'll mix it up. Oh my gosh, our numbers are fading. All right, well, it's 9 o'clock, so just because we can't see each other in person doesn't mean we can't have the simultaneous sip. So if you have your coffee ready, feel free to join me in the simultaneous sip. Okay, that was nice. Maybe something we could do for the simultaneous sip is maybe you can just leave comments in the live chat that you maybe type the word sip if you joined in. I guess before we get to the math, we should talk a little bit about the plan for the rest of the semester. I sent Friday, but the following Friday, and it's going to be a take-home, so you'll have it over the weekend, okay? And you'll be allowed to use your notes, and you're allowed to use the book, but obviously you can't be using tutors, and you can't be using Dr. Google to help you out. But yeah, you should. So expect some more information on that coming up. You have a homework due on Thursday. So start working on that. I have office hours tomorrow and Thursday, so we could talk about the homework then if you want to. Oh yeah, so what you'll do to submit your homework is you'll take a picture of it and then post it to Canvas as a PDF. Okay, so I sent out 2 names of apps that do that easily, yeah, whatever your favorite app that turns pictures into PDFs, that should be fine. And if you have issues, just email me. We'll be able to figure it out. I'm going to be very lenient with everything at first because this is kind of a weird situation. And then the quiz on Friday, I'll give you an hour to take the quiz. It's going to be the same format as our normal quizzes, so it should only take you 5 to 10 minutes. But I'll give you an hour so you can figure out how to upload it, and it's going to be the same thing. Take a picture and post it to Canvas. But we'll talk about that more on Thursday and Friday. Okay, so I know it's been a while since we've thought about linear algebra, but we should think about it. Another thing before we get to the work again is, so my lighting in my studio here is not perfect. I'm going to try to stay out of the camera as much as possible so we could read it. But if this is a disaster, I'm going to be sending out a survey in the next few days to kind of get some feedback on how our setup is. So I'm flexible in terms of willing to change. Okay, I just rambled on for 4 minutes. Let's get started. So this is section 4.7. And if I'm writing too small, just write it in the comments. I'm going to be checking the comments throughout the lecture. Okay, this is change of basis. And before we get to this information, the format of the class is going to be the same. I'm going to, give a little bit of background, definition, theorem, and then example. And if you are willing to share some ideas in the chat of how you would start the example, that's great. But I understand that it's hard to type in the math. But like during this exam, I'll give you a few minutes to work out examples on your own. And during that time, I'm going to be checking on the chat to see if anybody has any ideas they'd like to share. Okay. And I also have no clue how long this class will be. I'll make sure we're out by 9:50, but maybe it's short. Who knows? Okay, so this is change of basis. So in some applications, a problem could be described initially in terms of one basis, but maybe it's easier to answer the question in terms of another basis, right? We had these bases. They were linearly independent sets that span whatever subspace they're living in. But we could describe coordinates in terms of many different bases. I'm going to send out a video later today by 3 Blue, 1 Brown that gives a great visual of what a change of bases is. It's easier to see than drawing on the board. So in some applications, a problem is described in terms of a basis B, but it's easier to answer if we look at it in terms of a basis C. So what we're going to do is we're going to come up with or talk about how to take our B coordinate vectors and express it as a C coordinate vector. Here, B and C are just 2 different bases. Okay, and you may have to look back in your notes to remind yourself what the B coordinate vector was, but it basically was our way of taking our vector in, let's say, R3. I guess let me be in the camera so you can see me talk with my hands. We could take like a vector in R3 and express it in terms of whatever bases are. We like our default setting is to say, how many, like the vector, just for example, the vector 3, 2, 1. We say it's like 3 times the first basis vector, or I guess we could write it like this. Right, I'm going to erase this in a second, but our default setting is the coefficients tell us how many of the first standard basis vector, how many of the second standard basis vector, and how many of the third standard basis vector. But we could do this for any basis. So each vector is assigned a new C coordinate vector. And so in this set, we study how our C coordinate vector and the B coordinate vector are related. Okay, so I'll give you a second to kind of catch up with these notes. But that's the big idea. We're gonna express some vector x in terms of a B coordinate vector or in terms of some C coordinate vector, and we'll see how those 2 coordinate vectors are related. Okay, so we'll start by looking at an example. So I'm going to block this part of the board, so you may have to catch it once I move. B1, B2, and C, BC1, C2. For some vector space V, okay? we have that B1 is equal to 4C1 plus C2, and B2 is equal to minus 6C1 plus C2. Suppose we have a vector x, which is 3b1 plus b2. We want to find, okay, so another way to write that, i.e. the b coordinates of x is 3, 1, right? Remember the b coordinates just tell us the coefficient of b1 and the coefficient of b2. The question is find the c coordinates of x. Okay, so that's our question. I'll give you, let's say, a minute to think about this, and please write some comments in the chat if you have if there's anything you want me to clarify, or if you have some thoughts on how we're going to solve this problem. But there's about a 30-second delay, so it'll take me a second to see your comments. And you never realize how awkward silence is until you have to teach. Look at multiply. Yeah, that's a kind of the right idea. Basically, what we want to do is express x in terms of the c vectors, and we know that b1 is equal to 4c1 plus c2, and we know that b2 is equal to negative 6c1 plus c2. So let's just substitute. What we could do is substitute those values in for b1 and b2. Okay, so that's how we're going to do this. Okay, so we want to find, and I'm going to kind of write it out formally, or kind of in a funny way, because it's going to be easier to generalize. Okay, so x sub c, so the c coordinates of x, well, that's just the same thing as the c coordinates of 3b1 plus b2. Okay, and we saw in section 4.4, so you could look back in your notes if you don't believe this, that we can, this coordinate map is a linear map. So we could rewrite this as 3 times the coordinates of b1 plus the c coordinates of b2. And we know from the information given to us that the c coordinates of b1 are 4, 1, and the c coordinates of b2 are negative 6, 1. So let's sub those in. Okay, and I know that now we could simplify this, but for the sake of generalization, and whoever upvoted this video, let me know. I'll give you an upvote right back. Okay, for the sake of generalization, we could rewrite this as the matrix 4, 1 minus 6, 1 times the vector 3, 1. Right? See if you believe that that's true. And now maybe you're wondering, why are we doing it this way? You'll see once we do some more examples that it's best to go with this method. And if we were to do this multiplication out, we would get 12 minus 6 is 6, and 3 plus 1 is 4. So 6, 4. Okay, and so the way we got the c coordinate vectors of x is we had a matrix where we had, it turned out it's the same thing as taking a matrix whose first entry was the c coordinates of b1, the next entry was the c coordinates of b2. I don't like being so close to the webcam, sorry. And multiply by the b coordinates of x, and we got our answer. Okay, and this generalizes when we have more than just two vectors. So we could write that as a theorem. How did we get the vector 4, 1? That's a good question. So we got that from, let me get a new color. So this equation here gives us 4, 1, right? It tells us B1, that it's 4 times C1 plus 1 times C2. And then this equation here gives us this part. Before I move on, are there any other questions? Okay, well, I'll give you a second to kind of catch up with these notes, and I'll start erasing some of this. If you're ever wondering what the apartment of your math professor looks like, this is what they always look like. They just have a bunch of whiteboards everywhere. So if there's any math professors, or I see my friend Andy is in the chat, I'm sure he has the same thing. Is 6, 4 your values for C1 and C2? Yeah, so this is saying a way to interpret this is x is equal to 6 times C1 plus 4 times C2. Yeah, so if our first step was just replacing B1 and B2 with this information here, we would have gotten this equation, and then we could have gotten our answer that way. But the reason why I'm writing it out, this way is our next theorem will tell us that it generalizes. And again, I'm sorry for being so close. Oh, 4 upvotes now. So close to the webcam. It's going to take some getting used to. Andy says, I was hoping to get a chalkboard wall, but instead I got a whiteboard wall. Yeah, you can't always get what you want. Sometimes you got to just settle with whiteboards. Okay. So the theorem tells us how to do this in general. It says so B will be now have, instead of just 2 vectors, we'll have n vectors, and C will also be a basis with n vectors. Okay, so we'll let B and C be just 2 bases of some vector space V. So what the theorem says is then there is a unique n by n matrix, which we denote by P sub C left arrow B. Okay, so it's the matrix we denote by P, and the bottom part tells us that the basis is changing from B. Our coordinates are going to change from B to C. So I know we kind of write it in the opposite order of what we would want, but it's the arrow points in the direction of C. Okay, so there's this unique matrix that satisfies this equation. The C coordinates of x are equal to this matrix times the B coordinates of x. Okay, so this is a matrix here. Again, I'll take out the green marker. So there's a unique matrix that satisfies our C coordinate vector is equal to this matrix times our B coordinate vector. And then this second part of the theorem tells us how do we actually get the columns. The first column is the C coordinates of B1. The second column is the C coordinates of B2, and so forth. Okay, and so this is how we get that change of coordinates matrix. And so just in plain words, the columns of this change of coordinates matrix are the C coordinate vectors of the vectors from B. Okay? And so let's give a formal definition of this matrix so we can give it a name, and then we could maybe look at an example again. So before I get in the way, I'll give you a second to ask questions and write this down. Okay. So we call this matrix piece, we call this the change of coordinates matrix. Okay, so if you hear the term the change of coordinates matrix, it's asking you to find this matrix where the columns are made up of the C coordinate vectors of the basis B. And so what does this do? Multiplication by this matrix maps B coordinate vectors to C coordinate vectors. And one more fact, to get the change of coordinates matrix from C to B, so if we switch the order, all we have to do is find the inverse of this matrix. Okay, so if there was a question that said, for instance, find the change of coordinates basis from B to C, and then find the change of coordinates basis from C to B, you'd have to find one of them and then just find its inverse. Okay? So that's kind of the big idea here in this section. So let's take a look at another example. And I'll give you a few minutes to work this one out. So while I'm writing out this example, maybe you could try to catch up on the notes and feel free to ask some questions I have my eyes on the chat. Don't worry. So the example is let B1 equal negative 9, 1. Okay, so far we have these, and I'll get out of the light here. I got one of my spotlights down below here, if you can't tell. B1 is negative 9, 1. Let me get out of the way of the light. B1 is negative 9, 1. B2 is negative 5, negative 1. C1 is 1, negative 4. And C1 is 1, negative 4, and C2 is 3, 5. So the question is, and you could check that B and C are bases. We're not going to go through that, but you check that they're linearly independent and span all of R2. So B and C are bases for R2. And the question is, find the change of coordinates matrix from B to C. Okay, that's the question. And so I'll give you, let's say, a minute or so to ask some questions or share some thoughts on how you solve this. And then we could talk about how to solve this. Okay, so we wanted this theorem here to solve our problem, right? It tells us exactly the change of coordinates matrix from C to B, or from B to C. But the question is, what are the C coordinates? What are the C coordinates of B1 and B2? That's really what the question boils down to. Okay, so let's talk about how we're going to do that. Okay. So let's talk about this. So we need to find okay, so that's our goal, right? If we could find the C coordinates of B1 and the C coordinates of B2, then we're done. The theorem says our matrix is just, the columns of our matrix are just these vectors. Okay. So now the question is, how do we find these? Well, we'll give them names. So we'll let the C coordinates of B1, we could call maybe x1, x2. And the C coordinates of B2, we could call y1, y2. And so by definition, what this means is that B1 is equal to oops, they're not vectors. By definition, B1 is equal to, well, maybe I'll write it out even one more line before we get to this. So ignore that. X1, C1 plus X2, C2. And B2 is equal to Y1, C1 plus Y2, C2. That's what it means to be C coordinate vectors. And we could write this as a matrix equation. So these are both matrix equations, and we know how to solve those. We could just set up an augmented matrix and row reduce until we get reduced row echelon form, and we could just read off the solutions. Okay, so to solve these matrix equations, what we could do is, so to solve this, we could either have two separate augmented matrix and row reduce both of them, or what we could do is have, instead of just a rightmost column be the solution column, we'll have two solution columns. Okay? So to solve this, row reduce the augmented matrix C1, C2, B1, B2. Okay? Because this will, what we're doing here is just solving, we're going to be solving two systems at once. Okay, you could treat it separately as two separate problems. Set up an augmented matrix here, set up an augmented matrix here, and solve them. But it's easier to work it this way. So C1 and C2 were given. And B1 and B2 were also given. And what we want to do is we want to row reduce this until we have the identity, the 2 by 2. So I'm not going to go through all the row reduction because I don't have that much whiteboard space. But it row reduces to 1, 0, 0, 1. So here's the identity. And we get 6 minus 5, 4 minus 3. So what that tells us is that x1, x2, which is our B1, our C coordinate vectors for B1, is 6, negative 5. And then our C coordinate vectors for B2 is 4 minus 3. And then by our previous theorem, these vectors make up the columns of our matrix. Systems using augmented matrices twice, but we'll see that it's easier to just treat it as one large augmented matrix and row reduce it once. Okay, so I'll give you a minute or so to ask some questions and kind of catch up with these notes. But then we could generalize this example and then do one more example. I'd say this is a pretty good crowd so far today. 18 viewers. Not bad. I have 30 students, but it's okay. Okay. So no questions? I'm back. Okay. So in general, the way we could find the change of coordinates matrix. Oh, I see a question. Can you explain again what P sub C here is? Yeah, it's a matrix that would, when we multiply, let me get out of the way. It's a matrix that if we multiply this matrix to the B coordinate vectors, what we get out is the C coordinate vectors. Okay, so it allows us to map from one coordinate system to another coordinate system. If you're, I know many of you are not taking Calc 3, but this is an idea that you see a lot when you're parameterizing curves. You have the unit tangent, unit normal, and unit basis vectors, and it's good to kind of map in between them. And this is kind of the method there. So it's this process you'll see a lot in physics. The video I'm going to send out this afternoon, it's like a 15-minute video. Gives us a nice visual of what's happening here. Yeah, so you're right. So sometimes it's easier to use the C coordinate vectors as opposed to the B coordinate vectors in certain examples. In this case, there's nothing easier than between the B's and the C's. It's just we're practicing finding this matrix. Okay. So the way we get, if we start with the matrix C1 through Cn, B1 through Bn. So in general, this matrix row reduces to the identity and then the change of coordinates base matrix from B to C. This is if you want to find the change of coordinates matrix from B to C, start with an augmented matrix that has our C basis vectors followed by our B basis vectors, and then row reduce until we get the identity on the left, and what's left over on the right is the change of basis matrix from B to C. Okay, so this is our method for finding the change of coordinate matrix. Okay, so let's look at an example. Okay, so B1, B2. My brother's in the chat. B1, B2, C1, C2 are here. And we want to find the change of coordinate matrix from B to C. So what we'll do is we'll just use this fact here. Okay, so we'll write out an augmented matrix that has columns C1, C2, B1, B2, row reduce it until we get the identity matrix on the left, and we're left with the change of coordinate bases here. Okay, so here's the example. We want to find the change of coordinate matrix from B to C and also the one from C to B. And I'll just work it out right now, but feel free to try this on your own after class. So we'll start with this one. Mix it up a bit. So to get the change of coordinate basis from C to B, we start with the matrix B1, B2, C1, C2. And we'll row reduce it until we get the identity as our first two entries, and whatever is left over at the end here will be our change of coordinate matrix. Okay, so when we do this, you can check this on your own. We get 1, 0, 0, 1, and 5, 6, 3, 4. Okay, and so we can conclude from this fact here that our change of coordinate matrix from C to B is this matrix here. Okay, and now while I'm erasing stuff, I'm going to ask a question. So feel free to type in your answer. How do we get, what's an easy way to get the other direction, the change of coordinate basis from B to C? You may need to look back in your notes to see how do we change the direction easily. So from here, we could conclude five, 6, 3, 4. Yes. Look at you all answer have great answers. Maybe the online setting helps everybody to encourage these great answers. But yes, all three of you, Maddie, Shutong, and Miriam, you are correct. You take the inverse. Yeah, so let's just find the inverse. We could do the same process. And I'm just teasing you. The reason why I'm joking is sometimes, especially in the 8 o'clock class, everybody's a little bit tired. 9 o'clock, we're a little bit more awake. But yeah, so let's just find the inverse. So it's the inverse of this matrix. And Miriam, I agree. I would also rather be on campus. My brother claims to know how to do these problems, but I don't know. Okay, and so we had a formula for finding the matrix, for finding the inverse of a 2 by 2 matrix. Okay, so that was this is equal to 1 over the determinant. So the determinant here is 5 times 4, which is 20, minus 6 times 3, which is 18, times the matrix where you switch the main diagonal entries and you turn the other ones negative. I'll tell you in a second, Shutong. Let me just write this down. So this works out to be 2, -3, -3 halves, 5 halves. So how did I get this matrix here? Well, it's exactly this matrix here. So if you just row reduce this until we get the identity as our first two columns, what's left over on the right is the change of coordinate matrix from C to B. Okay, and that's what that's what this panel here says. Okay, and so yeah, I have an example on YouTube doing a question similar to this. So feel free to take a look at that. I'll stay here for the next 5 minutes answering any questions, but that's all I have for material today. So thank you for showing up and interacting with me on chat. I'll see you all tomorrow when we start chapter 5. Okay, so bye-bye. Unless you have questions, then I'm still here. Seven upvotes. It could be my most upvoted. Yes, Lisa. These will be on YouTube, I'm hoping immediately. It should just be on the channel. If it doesn't go up automatically, I'll post it by noon. Sorry, I said Liza. Never mind. From the first example we did in class, can you show the change of coordinate matrix? Can you? Okay, hold on. Noah, I'll answer your question in a second. Cal, let me see. From the first example we did, let me get my notes. Can you show the change of coordinate matrix? Oh, did you just miss it? Yeah, so from the first example, Cal, it was this. Is that what you're asking? 4, 1, negative 6, 1. And so you could get it using the same method we just did here. And Noah says, can you show for row A of a matrix how to write out the bases? Yeah. Noah, so what you do there is you take your matrix and you row reduce it to echelon form. You could go to reduced row echelon form. Just so you could row reduce it to any echelon form, and then a basis for the row space is just the non-zero vectors. Of the echelon form matrix. Does that make sense? Yeah, and if it doesn't, think about it a little, and we could Zoom later to explain if Zoom's easier. Send me an email if you need a little bit more help. Okay, I got to get ready for calc, so I'm going to end the stream here. Thank you all for coming. I will see you tomorrow.